Hello everyone, so I'll be talking about a static equilibrium problem that you might encounter in one of your exams or your homeworks or just any discussion sessions that you might have. So let's just jump right into it. So in the figure below, an 80 kilogram construction worker sits down 2 meters from the end of a 1450 kilogram steel beam to eat his lunch. The cable supporting the beam is rated at 15,000 newtons. Should the worker be worried? So since this is a static equilibrium problem, we have to worry about three conditions. So the first condition is that the sum of the forces in the x direction have to equal 0. Along with that, the sum of forces in the y direction also have to equal to 0. And last but not least, the sum of moments about any point have to be equal to 0. So those are our three main conditions. Now, if any one of these three conditions are violated, then that means that we don't have static equilibrium. So first thing, as always, to make things easier to visualize, we always want to draw a free body diagram. So pretend that this is our beam, and let's break our forces down. So we have a cable going 30 degrees from the horizontal directed here towards the wall, and we'll call this T, angled at 30 degrees. We have some unknown Y support force along the wall, and also lateral X force as well, and that acts along this this attachment point between the wall and the beam. And now the two other forces is we have the weight of the person, of course. Let's redraw that one. We have the weight of the person. Let's call this weight W sub P. And we have, of course, the weight of the beam. Now, which acts at 3 meters. And 2 meters from this end. And last but not least, we know that this is indeed 6 meters. Okay, so now that we have a free body diagram here, let's solve for the sum of the moments. Now, when we apply this third equation here, we can apply it to any single point that we want along this beam. Now, if you're wise about where we pick, we can effectively eliminate more forces that we may not have to worry about. So for example, if we pick the pivot point to be along this other end of the beam where the cable is tethered to, here, we know that any force acting directly on a pivot point generates zero moment because there is effectively a zero moment arm. So anything times 0 is 0, and that causes zero moment. Now, because if you pick it here, we know we have to worry about the moment due to this WP, this WB, and maybe two more forces. And if you pick similar to that, if you pick it along where the person is standing, the location of WP, then we have this tension force to worry about, and these three other forces as well. But if we pick it about this point over here, and let's call this O because I do want to pick that as our pivot point, then we effectively know that the a sub y and the a sub x is canceled out, and the only forces that we have to really worry about is WB, W sub P, and tension force. So these are our three forces. So now let's solve for that sum of moments equations along this point O. So one thing to remember is that typically the positive direction is oriented counterclockwise with regards to moment, so we'll keep that consistent throughout our problem. So going right along into it, we have sum of the moments is equal to 0. Now, dealing with this first force, the weight of the beam, we have a 3-meter moment arm, and it's trying to pull this beam downwards. and that will cause this beam to rotate counterclockwise with respect to this point O. So that will be a negative with a 3-meter moment arm and multiplied by the weight of that beam. And similarly, we have the weight of the person. Now it says 2 meters on the problem, but we have to remember that with respect to our free body diagram here, the moment arm is actually 6 minus 2, or 4-meter moment arm. So we have 4 times WP, and this also wants to pull it down and rotate it clockwise. Sorry, yeah, clockwise. So that will be minus, that will be minus, and again, counterclockwise is positive. Now we're done with clockwise moments. Now for the counterclockwise, we have this tension force over here. So we have a positive wanting to pull this back up. The moment arm is the whole length of this beam, so it'll be 6 meters times T. And since this is angled, we only want to worry about the vertical component of this force. So in this case, that will be sine 30 degrees. And in order to have static equilibrium, we know that the sum of all these moments generated have to equal 0. Now, we know W sub B, which is the mass of the beam times gravitational acceleration constant, which is 9.8. And we also know the weight of the person, which is 80 kilograms times g. So we could solve this equation and solve for this t. Now, writing this out, we have times 1450 times g minus 4 times 80 times g, and a positive, because the moment is counterclockwise now, 6t times sine 30. And this might be just helpful to know or memorize. This sine 30 degrees is always equal to 1/2. Just trig knowledge, and we effectively get that this whole thing is equal to 0. Now, we know every single thing here, and we're just going to solve for our t value. And if we plug this in, we actually get that this t is 15,255 newtons. Now, what does this mean? We have a cable supporting the beam, which is rated at 15,000 newtons, but the tension that we actually get out of this system, where this construction worker is placed 2 meters from the end of the beam, we require a tension force that is 15,255 newtons, which is greater than the allotted or the rated 15,000 newton force. Now, because the tension force that we get out of this is greater than the rating, that means this cable will fail or snap or break or whatever happens, and this will no longer be able to support the length of this beam or the weight of this beam and the person anymore, which means that this beam will effectively collapse, and along with that, the construction worker. So that means that this system is not safe, and the worker should indeed be worried. So yes, he should be worried. Now, a few other things to note is, I know that I mentioned the 3 conditions here. The sum of f sub x being equal to 0, the f sub y equaling 0, and the sum of moments all equaling 0. But as long as any one of these conditions is violated, or we reach a condition that these equations don't work out, like we could even solve for the y directional force is equal to 0. and try to solve it from there. We could have done that, but that might have resulted in more work because we don't exactly know what our a sub y and our a sub x forces are. So a really powerful tool in solving these quantitative equations is picking your pivot point to not oversimplify, but greatly reduce the amount of equations or unknowns that you have to solve for. In this case, if we picked our pivot point wisely, so we only had to solve for one equation. So I hope this helps.